Hello, Bobcats. This is Chemistry 2342, and we're going to start Chapter 19, Condensation Conjugate Addition Reactions. And so this is a continuation of Chapter 18, which involved enolates, and so we're going to look at some additional reactions we can do on these. Okay. The first thing we're going to talk about is the condensation reactions, and in the condensation reactions of these carbonyl compounds, an enolate or the enol of one carbonyl compound reacts with the carbonyl of another compound, joining the two together. Typically, a small molecule is distilled out of this and then therefore condenses in the distillation portion of the apparatus, driving the reaction to completion. So the first example I want to talk about is called the Claisen condensation, which forms an alcohol. So in this case, we take an ester with two alpha hydrogens. We use a base to deprotonate that to form the enolate. The enolate then reacts with the carbonyl of another ester, liberating our diketo compound and our alcohol. Okay. So let's talk about that in a little more detail. When the proton is removed from the alpha carbon of one of the esters, it creates the enolate that can then react with the other ester. And then in the process of it reforming the carbonyl compound, it spits out ethanol. Note that when we do this, we always spit out a small molecule like water, but in this case, it's ethanol. We typically use the same base as the alkoxide as the ester we're using. So in this case, we're using the ethyl ester, so we want to use the ethyl alkoxide. If we had the methyl ester, we want to use the methyl alkoxide. Okay, and in the last step of this reaction, we acidify it to gain our keto species and then get our alcohol out. So for the best yields on this, it's great to have two alpha hydrogens to do this Claisen condensation, and I'll show you why in the mechanism. Okay, so let's look at the mechanism in more detail. So the first step, of course, is deprotonation of an alpha proton to generate our alkoxide, our enolate. In this case, we're using methoxide because we have a methyl ether, okay, a methyl ester. So once we generate this alkoxide, it can then attack the carbonyl of another one of the esters, generating this tetrahedral intermediate here with the anion of the oxide up here and a methyl ether here. When the electrons of that alkoxide kick in, it kicks out the methoxide, generating our neutral species here. Okay, so that is the net reaction of the system, but there's an additional step we're going to end up doing. Okay, so to have a successful Claisen condensation, we need to use this methoxide we formed to actually generate this anion here, this diketo anion. When we generate that diketo anion, it is now no longer nucleophilic because it's of the sterics demand, and it stops the reaction there. So what we will able to do is by deprotonating that second alpha hydrogen here, we generate this anion and we can distill off the methanol. Once we're distilling off that methanol, it stops it as this anion here, and then at the end of the reaction, we add acid to generate our dicarbonyl compound. Okay. Now, if we have two esters on the same compound, we can do an intramolecular Claisen condensation, and this is called the Dieckmann condensation. This only works to form 5- and 6-membered rings. 4-membered rings are too sterically demanding, and they'll be too tight, and 7-membered rings tend to be too entropically driven away from that, so we can form 5- and 6-membered rings. But the mechanism is the same as in the condensation reaction, except that the enolate we form is on the same molecule that closes the ring. So let's look at that mechanism here. In this case, we have the methyl ester here, so we're going to use the methyl alkoxide. We form the enolate, and then that enolate can form this 5- or 6-member transition state where it forms the new carbon-carbon bond, giving us our methyl ether and our alkoxide. Then when the electrons kick in from our alkoxide, it kicks out the methoxide here as our product. And then this can actually deprotonate this right here to be able to distill off the methanol. And then when we acidify at the end, we regain this alpha proton. Okay. So most of the time we want to use it where it has two alpha hydrogens, okay? And the reason we need to do that is because it's easier to use those two alpha hydrogens to drive the equilibrium of the condensation to the products. If we only have one of those alpha hydrogens there, then we have to use a much stronger base than alkoxide. And our much stronger base we typically go to in enolate chemistry is LDA. So in the case of this substrate here, we have a di-substituted carbon here, which means we only have a single alpha hydrogen. We use LDA to deprotonate it to create our enolate here. And then because we created this all at once at low temperature, we can now either add the same carbonyl compound or a different carbonyl compound to generate our product. And so unlike the equilibrium reaction where it's typically done where you're reacting two of the same thing, we can actually use that single alpha hydrogen to do what we can do adding a different one in. So if we make our enolate first, then add our compound here, we're going to generate this in high yields. And notice we do not have any more alpha hydrogens here or here, so the reaction does not progress any further. Okay. Now we can do what is called a crossed Claisen condensation. In a crossed Claisen condensation, you use two different esters, okay? Now, the way we typically do that is we have a ester that has two alpha hydrogens, and then we have another ester that we use in excess that has no alpha hydrogens. This works great because you can only form the enolate with the one with the two alpha hydrogens. And then because you have the other carbonyl compound in excess, it's more likely that the enolate driven will come and react with that compound. And then when we acidify at the end, we generate our cross Claisen condensation product, and we have it in very decent yields. Okay, so what if we did this, instead of using esters, we started with aldehydes and ketones? Well, when we start with aldehydes and ketones, we actually call that the Aldol addition, okay? It was traditionally started using aldehydes, and so in the presence of an aldehyde, we end up making an aldehyde alcohol, and therefore it's called the Aldol reaction, okay? So in the traditional Aldol reaction, we take an aldehyde right here with two alpha hydrogens, and we create the enolate, and then that reacts with another carbonyl of another aldehyde to generate this beta hydroxy aldehyde, okay? Now, because this reaction is reversible, we tend to remove the product as it's formed, either by precipitation or other means, such that we can stop it at that reaction, because another equivalent can come and attack this carbonyl if necessary. Okay, so let's look at the mechanism of the Aldol condensation, how it was a little bit different than the Claisen. So in this case, we use a base like hydroxide to generate our enolate here. And our enolate, of course, goes back and forth between the keto and enol forms, okay? This anion then can attack the carbonyl compound, giving us our intermediate compound with the alkoxide right here and our ketone. This can then be protonated by water to protonate the alcohol here to generate our beta hydroxy aldehyde here. Okay. Note that we can use ketones for this, but they react more slowly than with aldehydes because of sterics. Okay, and because this reaction progresses so easily in the presence of an aldehyde, this is why aldehydes didn't work very well when we were first generating enolates in chapter 18, because they would so rapidly react with themselves in an aldol addition reaction that they would not be useful as enolates except in this specific form of the reaction. And that ends section 19.1, condensation reactions.